Good morning. My name is Doug Knisely, and I'm with Qualcomm's Industry Standards Organization. I'm also Qualcomm's representative on the OAI Advisory Board. Today, I want to talk about OAI's role in establishing a 5G reference architecture for the emerging 5G industry. Today, 5G is rolling out around the world with wide adoption, much faster than previous generations. And 5G brings with it a lot of new capabilities and enablers for radically new use cases that were never possible before in previous generations. This includes things like factory automation, fixed wireless access with more capacity and speed than were ever imaginable in previous generations, smart transportation, and Internet of Things on a massive scale beyond anything that's ever been conceived. But most importantly, 5G has extensive features to support private networks, 5G private networks, operated in many different kinds of environments, and also, very importantly, the integration of public networks and private networks through techniques like network slicing. 5G adoption is happening at a rapid pace and also accelerating rapidly with some 385 or more operators investing around the world, hundreds of millions of devices already shipped, and billions coming in the next few years. So this is significant progress at a rate that exceeds any other previous generation that we've seen. At the same time, the radio access network architecture and deployment models are evolving equally rapidly. Today, most of the world is based on traditional RAN architectures where there are basically closed systems that include a core network that may have a somewhat open interface via the backhaul to the RAN, but the entire RAN is implemented by typically a single vendor or a small number of vendors working closely with many proprietary interfaces and not a lot of flexibility for choice of components that can be integrated together. The trend over the past few years has been to move to what is sometimes called centralized RAN or cloud RAN, where some of the centralized control for the radio access network or the RRU is moved to a centralized location, generally with a proprietary backhaul out to the radio heads, which are lighter and simpler generally. And then with the same interfaces from the radio access network back to the core network. It's a big improvement, allows the use in some case of commercial off-the-shelf or nearly commercial off-the-shelf gear for economies of scale and centralization, the advantages of centralization of some of the functionality. But it doesn't yet fully address the ability to mix and match vendors and component selections. The latest innovation in the evolution of RAN architecture is the so-called virtualized RAN or vRAN, sometimes called Open RAN or ORAN, along with mobile edge computing, where you're pushing more of the computation on commercial off-the-shelf platforms down closer to the edge, closer to the radios. In addition, a key aspect of this is to open interfaces between the centralized part of the radio access network, or the CU, which is implemented on commercial off-the-shelf hardware, so it's all software based. And it has open interfaces out to a distribution unit, which then interfaces to the radio unit, or typically interfaces to multiple radio units, which are small elements right located where the radio is. All of the interfaces from the RU to the DU to the CU and back to the core network are open, and as well as there are standards developing for managing and orchestrating all of this using many more commercial off-the-shelf technologies as platforms, especially for the DU and the CU. The core network typically today is already implemented in a virtualized manner on commercial off-the-shelf hardware. This will allow better coordination amongst equipment from multiple vendors, scalable capacity and densification of the network, faster deployments. It will lower latency by pushing computations out closer to the edge, and it will enable new use cases, as I discussed in the previous slides. The research and development landscape is complicated for 5G. Industry standard efforts for 5G are mature and also evolving rapidly to new capabilities. 3GPP is moving from release 15 and 16, which complete a solid base for 5G functionality, into release 17 and 18 that are adding many new features for new use cases rapidly. The O-RAN Alliance is developing interfaces for the RAN intelligent controller, which allows AI to be introduced to increase efficiency and flexibility and control, and as well as filling out the details for the OANM orchestration and management functionalities. And developing complete set of open interfaces for RAN disaggregation, particularly between the RU and the DU and the CU. Other groups like Small Cell Forum are developing interface specifications for particularly important APIs such as FAPI and NFAPI that are the definitive interface between the physical layer and the MAC layer. And many commercial implementations, as you know, are proceeding rapidly, some proprietary, some partially open, and many focusing on this new virtualized RAN or open RAN model. These virtualized or disaggregated RAN architectures are revolutionizing network deployments, enabling new use cases, allowing more variety of technologies for massive MIMO and millimeter wave radio heads as those spectrum opportunities are developed around the world. And new elements such as the RAN intelligent controller and the CU and DU and RU, and new deployment models on commercial off-the-shelf software based on containerized and virtualized software, and interfaces for the front haul, the FAPI and NFAPI interfaces between the PHY and the MAC, and the management and orchestration interfaces, and the AI interface to the RIC, which is called E2 in O-RAN. And reference architectures, including open source implementations of all of this, are needed to support industry and academia. But these efforts have lagged partially because of the incredibly rapid pace of standardization and implementation, but also because it's just a lot of work that needs to be done and the resources need to be identified. To address this, OSA has launched the 5G RAN and core network programs to accelerate the efforts to develop a full stack implementation. And 5G is a proud sponsor of these efforts. The OAI 5G core network and RAN stacks are the foundation of a 5G reference architecture. And they define basically the 7-layer model from the physical layer up through the core network services. In addition, OAI is planning to develop interfaces such as the E2 interface out to the O-RAN developed RIC element, the RAN intelligent controller that adds AI intelligence. This defines the hooks in the RAN that implement or instantiate the intelligent actions driven by the RAN intelligent controller. And OAI also has a close relationship with TIP to continue to support the open core network activities in TIP and to maximize the synergies and reuse of open source components between these projects. And there are many other projects, particularly in the management and orchestration area, in ORAN, ONF, ONAP, and many others, to complete the picture of making a manageable, complete reference architecture and with associated open source implementations that'll be available. And there are many benefits for this for industry and academia. This can serve as a core for 5G research efforts in universities and even in companies that are doing research. It unifies the open source efforts between ORAN, OAI, TIP, ONF, and other organizations, avoiding duplication of effort and ensuring that the interfaces and APIs are compatible, consistent, and integration testing is done for those. It provides a framework for incorporation of commercial or research components. So one can take the open source framework that has been developed out of OAI and substitute other layer 1 implementations if you have a PHY product, or layer 2 implementations, sorry about that, little extra clicking, into the mix. And it improves interoperability and integration of component technologies by encouraging the projects to integrate and test both within the projects as well as externally in the R&D efforts that are using the code. It's important to note that the most significant, at least in Qualcomm's view, enabler that OAI can provide is to provide a reference stack that can be used for private networks. And there are integrated private networks that incorporate both private networks in, for example, in a factory to do industrial automation, integrated with public networks to share spectrum or to provide wide area services in combination with the local area services within the factory, as well as fully independent private networks that are implemented in factories and are completely self-contained and then integrate when devices move outside of the domain of the private network and need to use and access public network services and capabilities. In order to enable this vision, Qualcomm is a proud sponsor of OAI and the OAI 5G programs, and we encourage other companies and organizations to become involved and take advantage of these exciting opportunities that will enable industry, government, and academia efforts in the 5G space. Thank you very much, and my email is at the beginning of the talk. If you have any questions, feel free to get in touch.